Welcome to the Nocturnal Astronomer. I'm Atlas Reed. Whether you've come here to settle in after a long day, to quiet your thoughts before sleep, or simply because you found that the mystery of the universe has a way of making earthly worries feel smaller, you are in exactly the right place. Tonight, we are going to ask one of the most quietly captivating questions in all of astronomy. What if Earth had not one moon, but two? What would the nights look like? How would the oceans behave? How might life on this planet have unfolded differently? The answers take us deep into the mechanics of the solar system, the physics of gravity, and the long, slow story of how moons are made. Let's dive in. Part 1. A Moon by Chance. Most people grow up thinking of the moon as simply a permanent fixture of the sky, as natural and inevitable as the stars. But the moon is not a given. It is the result of an extraordinary event that took place roughly 4.5 billion years ago, when the solar system was still sorting itself out. The leading scientific explanation for the moon's origin is called the giant impact hypothesis. It holds that a body roughly the size of Mars collided with the early Earth in a glancing blow. That body is given the name Theia by researchers, after the Titan of ancient Greek mythology, who was said to be the mother of the moon goddess. The collision between Theia and the young Earth did not simply smash the two bodies apart. Instead, the impact ejected an enormous cloud of molten rock and vapor into orbit around Earth. Over time, perhaps just tens of millions of years in geological terms, that debris coalesced into the moon we see today. What is remarkable is that this scenario, as dramatic as it sounds, is actually considered fairly common in the broader story of planetary formation. Planetary scientists call the early phase of the solar system the period of heavy bombardment, when large bodies were constantly colliding, merging, and reshaping one another. Computer simulations of this era suggest that Earth could, in principle, have ended up with more than one moon. Some models show that the giant impact occasionally produces multiple bodies in orbit rather than a single large one. Whether they remain distinct or merge depends on a great many variables. A two-moon Earth is not, in other words, a fantasy. It is a plausible alternative history, one that planetary scientists have explored seriously using the same physics that explains what we actually observe. The universe is full of planets wearing more than one moon. In our own solar system, Mars has two small irregular moons named Phobos and Deimos. Jupiter has dozens. Saturn has even more. The idea of a planet with multiple moons is, from a cosmic perspective, entirely ordinary. It it is our Earth that is the slightly unusual case. So tonight, we are simply asking what might have been, and in doing so, we get to look more carefully at the moon we do have, at why it matters, and at how the subtle physics of gravity shapes the world we wake up in every morning. There is something quietly reassuring in that kind of exploration. The universe ran the numbers a certain way for Earth, and the result was one large, stabilizing moon. But it could have been otherwise, and understanding how is part of understanding why things are the way they are. Sit back, let your breathing slow, and let's follow this question wherever it leads. Part 2. How Moons Are Born. Before imagining two moons, it helps to understand what a moon actually is in the first place. The word moon is simply the name we give to any natural body that orbits a planet rather than orbiting the sun directly. Moons come in all sizes and compositions, from tiny captured asteroids barely a kilometer across to massive worlds larger than some planets. Our moon is large by any reasonable measure. It is about 1/4 the diameter of Earth, which makes it unusually large relative to its parent planet. Most moons in the solar system are tiny companions to large giants, like small stones orbiting enormous boulders. The fact that our moon is so proportionally large is actually one of the reasons scientists think the giant impact hypothesis is correct. A captured asteroid or a moon that coalesced slowly from a disk of gas and dust would likely be much smaller. Only a major collision could have produced something so substantial. The material that formed our moon came from both the impactor Theia and from Earth's own outer layers. This is why the moon's chemical composition so closely resembles Earth's mantle. The two bodies were essentially mixed together in the heat of the impact and then pulled apart again by gravity and rotation. In some versions of the giant impact model, the early moon formed from a disk of molten material that initially spread around Earth at high temperature and pressure. As that disk cooled over millions of years, particles began to stick together, growing into progressively larger clumps. This process is called accretion, and it is the same process that formed the planets themselves. It is, in a sense, the universe's preferred method of assembly. Gravity pulls small things together, and small things become large things, given enough time. Some researchers have proposed that the giant impact was even more energetic than traditionally thought, producing a rapidly spinning, partially vaporized Earth surrounded by a thick disk of silicate vapor. In this scenario, the moon formed from material that was almost entirely vaporized Earth rock, which would explain why the moon and Earth have nearly identical isotopic fingerprints. Whether one moon or two emerged from such an event would depend on how the debris distributed itself after the collision. If the disk had enough angular momentum and mass, it is possible for more than one condensation center to form, each eventually growing into its own moon. Computer models developed over the past few decades have simulated thousands of variations on the giant impact scenario. In some of those simulations, small companion moons do form alongside the primary body, though they tend to be much smaller and shorter-lived, often merging with the larger moon within a few million years. The universe does not always tidy up its experiments quickly. Sometimes two moons persist for hundreds of millions of years before their gravitational interactions finally bring them together. And on some other world, somewhere in the galaxy, that slow collision might still be playing out in slow motion. Part 3. The pull beneath our feet. To understand what two moons would mean for Earth, we first need to understand what our one moon is actually doing for us right now. The effects are more profound than most people realize, and they run through almost every aspect of life on this planet. The most obvious lunar influence is the tides. The moon's gravity pulls on Earth's oceans, creating a bulge of water on the side of the planet facing the moon, and a corresponding bulge on the opposite side due to inertial effects. As Earth rotates, different coastlines pass through these bulges, producing the regular rise and fall of sea level we call the tides. On most coastlines, this means roughly 2 high tides and 2 low tides every 24 hours. The difference in water level between a high tide and a low tide depends on the local geography of the coastline, the depth of the ocean basin, and the position of the moon in its orbit. During a new moon or a full moon, when the sun, moon, and Earth align, the gravitational pull of the sun adds to that of the moon, producing what are called spring tides. These are not named for the season, but for the idea of the water springing up higher than usual. During spring tides, high tides are higher and low tides are lower. When the moon is at a right angle to the sun, as seen from Earth, the solar and lunar pulls partially cancel each other, producing smaller tidal variations called neap tides. This interplay between the two gravitational sources creates a rhythm that repeats across roughly 2-week cycles. The moon also exerts a slight tidal pull on Earth's solid crust and on its atmosphere. These effects are smaller, but they are measurable. The solid Earth actually flexes by several centimeters in response to the moon's gravity, a phenomenon called Earth tides. Tidal friction, meaning the energy lost as the oceans slosh back and forth in response to the moon's pull, has a slow but measurable effect on Earth's rotation. Over billions of years, this friction has gradually slowed the rotation of Earth, lengthening our day from what was once perhaps just a few hours to the roughly 24 hours we experience now. In exchange, as Earth's rotation slows, the Moon drifts slightly farther away, gaining orbital energy. The Moon is currently moving away from Earth at a rate of about 3.5 centimeters per year, which is roughly the rate at which fingernails grow. This relationship between rotation, tidal friction, and orbital distance is a beautiful example of how interconnected gravitational systems evolve over time. Energy and momentum are conserved, just redistributed slowly and steadily across billions of years. Understanding all of this is important, because a second moon would not simply add its effects on top of our existing moons. The two moons would interact with each other and with Earth in a way that is more layered and more intricate, producing a system that none of us has ever experienced. Part 4. Two moons, two poles. Imagine for a moment that on some night billions of years ago, the giant impact had gone slightly differently, and two moons had condensed from the debris disk instead of one. What would that mean for the tides we feel on Earth today? The answer depends enormously on the sizes and orbits of the two moons. If one were large and close, and the other small and distant, the larger moon would dominate the tidal picture, much as our current moon does, with the second moon adding a secondary, weaker rhythm on top. If the two moons were of more comparable size and in similar orbits, the tidal situation would be considerably more intricate. There would be times when both moons pull in the same direction, and times when they pull from different angles, producing a constantly shifting tidal pattern rather than the relatively predictable one we have today. Researchers who study tidal mechanics can model these interactions mathematically, and the results suggest that a two-moon Earth would likely experience tides that vary more dramatically over time, with some tidal events being significantly stronger than usual when both moons and the sun align. Coastal ecosystems that depend on tidal rhythms would need to adapt to this more variable environment. On our Earth, countless species of marine animals and plants have evolved to synchronize their reproduction, feeding, and migration with the tidal cycle. In a two-moon world, those cycles would be more complicated. Some researchers have pointed out that tidal variety might actually encourage greater biological diversity in intertidal zones, because more variable conditions can create more ecological niches. Whether this is a benefit or simply a different kind of environment is not a question with a simple answer. On a practical human level, the tides would be less predictable, though not necessarily more dangerous. the maximum height of any given tide would depend on the positions of both moons, and coastal communities would need to track two distinct lunar cycles to anticipate flooding risk. There is something strangely calming about imagining this. Human beings have always adapted their ways of life to the rhythms of the natural world. A two-moon sky would simply give us more rhythms to observe, more patterns to learn, more reasons to look up. Ancient calendar systems were built around the moon because its phases are regular and visible. A two-moon Earth might have produced two distinct lunar calendars, interleaving with each other the way two slow musical rhythms can create an intricate, shifting pattern over time. There is something almost musical about it, actually. Two moons pulling on the same ocean, their rhythms overlapping and diverging, creating a tidal score that no one on Earth has ever heard, but that physics tells us would be real, and in its own way, beautiful. Part 5. The Sky at Night. Set aside for a moment all the physics and simply look up. Imagine the sky on a clear night in this alternate world. Two moons hang above you. Depending on their sizes and orbits, the sky might be dramatically brighter on some nights, with both moons full simultaneously. Our moon at full phase is the brightest natural object in the night sky after the sun, bright enough to cast faint shadows and wash out many stars. A second moon, if comparable in size, would make moonlit nights considerably brighter. The faint, diffuse glow of the Milky Way, already difficult to see from moonlit locations, might be almost entirely invisible on nights when both moons are full. On the other hand, there would be nights when one or both moons are in their crescent or new phases, offering skies darker than we typically experience. The contrast between a doubly moonlit night and a doubly dark one would be striking, a rhythm of light and darkness playing out over weeks. For nocturnal animals, this fluctuating light environment would be a constant factor in survival. Many animals already adjust their behavior based on the phase of our single moon, hunting more actively or hiding more carefully, depending on how much light the night offers. A two-moon world would add another layer to those adaptations. Human beings would likely have developed a rich mythology around the two moons. In many cultures on Earth, the moon is personified or deified, associated with cycles of time, fertility, and change. Two moons might have given rise to paired lunar deities, twin celestial guardians of the night, or two complementary forces in balance. There is a long tradition of humans finding meaning in the sky, of reading the movements of celestial bodies as signs and stories. A two-moon sky would have given our ancestors more to observe, more patterns to interpret, and more reasons to develop the careful attention to the heavens that eventually became astronomy. Ancient observers would have noticed that the two moons sometimes appear close together and sometimes far apart, that they occasionally pass in front of each other in what we would call a mutual occultation. These events might have held deep ceremonial significance, as eclipses do in many cultures on our Earth. The night sky in this alternate world would not be more frightening or chaotic. It would simply be richer, a sky with more going on, more light and shadow to track, more patterns to learn. For anyone who finds the current night sky beautiful, the idea of a second moon is less alarming than it is quietly wonderful. Looking up at any clear night sky, even our present one, has a way of quieting the mind. There is something about the sheer size of what you are seeing, the depth of it, that makes the problems of the day feel small and manageable. A sky with two moons would simply offer more of that. Part 6. Earth's Wobble and Stability. There is one effect of the moon that is less often discussed in casual conversation, but is arguably one of the most profound influences on life as we know it. The moon helps stabilize the tilt of Earth's axis, and that stability is part of what makes our climate livable. Earth's axis is currently tilted at about 23.5 degrees relative to its orbit around the Sun. This tilt is responsible for the seasons. As Earth orbits the Sun, different hemispheres are tilted toward or away from it, receiving more or less solar energy and producing the alternating warmth and cold that most of the planet experiences across the year. Without the moon, computer models suggest that Earth's axial tilt could wander considerably over millions of years, potentially shifting by tens of degrees in either direction. Such wandering would produce dramatic and prolonged climate shifts, making some periods of Earth's history far more extreme than anything we have experienced in the past several 100 million years. The moon acts as a gravitational anchor, damping the natural tendency of Earth's axis to drift. This is not a complete lock. The tilt does vary slightly over cycles of roughly 41,000 years, and this variation is actually one of the factors that drives the Ice Age cycles preserved in geological layers. But the moon keeps those variations within a modest range. Mars, which has no large stabilizing moon, has experienced much larger swings in its axial tilt over geological time, according to models. Some researchers believe this instability may have contributed to the dramatic changes in Mars's climate over its history. A second moon, if it were large and in a stable orbit, might actually enhance Earth's axial stability providing even greater resistance to tilt drift. Two gravitational anchors, rather than one, pulling the axis into alignment, could mean an Earth with even more predictable seasons over very long time periods. However, if the two moons were in orbits that interacted in elaborate ways, the net effect on axial stability could be more difficult to predict. The gravitational interplay between two moons could, in principle, introduce additional oscillations rather than simply adding more stability. This is one of the genuinely open questions in the study of hypothetical solar systems. Planetary scientists can model individual effects with great precision, but the combination of effects across billions of years involves so many variables that the outcomes vary significantly from one simulation to another. What we can say with confidence is that the moon's stabilizing influence on Earth's tilt is one of the quiet foundations of the climate we take for granted. It is another example of how the particular arrangement of things in our solar system, the specific result of all those ancient collisions, turns out to have been quietly working in our favor all along. Part 7. Roche Limits and Safe Distances. Not every orbit is a safe place for a moon to exist. There is a boundary around every planet, determined by the planet's gravity and the moon's own self-gravity, inside of which a moon cannot survive as a solid body. This boundary is called the Roche limit. Named after the French astronomer who calculated it in the 19th century, the Roche limit is the distance at which tidal forces from the planet would overcome the gravitational cohesion holding a moon together. A moon that drifts inside this boundary would gradually be pulled apart, its material spreading into a ring around the planet. Saturn's famous rings are thought to be, at least in part, the remnant of moons or other bodies that were broken apart in this way, or material that was never able to coalesce into a moon in the first place because it was always inside the Roche limit. For Earth, the Roche limit for a rocky body similar in density to our moon is roughly 10,000 kilometers from Earth's center. Our actual moon orbits at an average distance of about 384,000 kilometers, which is comfortably far outside this limit. Orbital mechanics shows that stable two-moon configurations are possible, but they require the moons to maintain significant distance in their orbits, or in specific resonant relationships where their orbital periods form simple ratios, like one moon completing two orbits for every one completed by the other. In a two-moon scenario, the orbital stability of the system would depend on the distances and sizes of both moons. If two moons were too close to each other, their mutual gravitational interaction could gradually destabilize both orbits, ultimately leading to a collision or the ejection of one moon from the system. These kinds of orbital resonances are not uncommon in the solar system. Jupiter's moons Io, Europa, and Ganymede are locked in a precise orbital resonance where for every orbit Ganymede completes, Europa completes 2 and Io completes 4. This resonance has persisted for billions of years and is a stable configuration. A two-moon Earth in a stable orbital resonance would be a long-lasting system, one that could persist for as long as our solar system itself. The moons would waltz around Earth in their fixed, rhythmic relationship, never drifting far enough to destabilize each other, never close enough to merge. There is something elegant about the idea of gravitational resonances. The universe, through nothing more than the mathematics of gravity, finds configurations that persist across billions of years, not because anything is trying to maintain them, but because they happen to be stable, and stability is its own kind of endurance. Part 8. What life might have found. The history of life on Earth is inseparable from the history of Earth's environment, and the Moon has shaped that environment in ways that are still being studied and understood. A second moon would have changed that environment, which means it might have changed the course of life itself. One important influence of the moon on early life is related to the tides. The intertidal zone, the strip of coastline between the high tide mark and the low tide mark, is one of the most biologically productive and ecologically creative environments on Earth. Life in this zone must cope with alternating immersion and exposure, with the rhythmic challenge of wet and dry. Some evolutionary biologists have proposed that the tidal zone may have played a role in the transition of early life from the sea to the land, providing an intermediate environment where organisms could gradually develop the ability to survive out of water for increasing periods of time. A two-moon Earth with more intricate tidal patterns would have had a more dynamic intertidal zone, one with greater extremes and more varied conditions across different coastlines. Whether this would have accelerated, delayed, or simply changed the character of life's movement onto land is not something we can know with certainty, but it is a question that researchers in astrobiology find genuinely interesting. The stabilizing effect of a second moon on Earth's axial tilt, if it enhanced stability, might have meant a planet with even more consistent climate zones over geological time. Long-term climatic stability is generally considered favorable for the development of elaborate life forms because it allows ecosystems to persist and elaborate over millions of years without being periodically reset by major climate upheavals. On the other hand, some researchers have argued that the occasional climate disruptions caused by axial wobble have actually played a role in driving evolutionary innovation, forcing organisms to adapt to changing conditions and thereby producing greater diversity over time. The relationship between environmental stability and biological diversity is one of the deepest puzzles in evolutionary biology, and a two-moon Earth provides a kind of thought experiment for exploring it. Different conditions do not necessarily mean worse conditions, just different evolutionary pressures producing different organisms. It is also worth noting that the moon affects the length of Earth's day, and the length of the day affects everything from photosynthesis to animal behavior to weather patterns. A two-moon system with different tidal friction characteristics might have slowed or accelerated Earth's rotation differently, producing a day of slightly different length. Over billions of years, even a small difference in the rate at which tidal friction slows a planet's rotation can compound into a significant difference in the length of the day. A world with a day of 20 hours rather than 24 would experience subtly different atmospheric circulation, different patterns of heating and cooling, and ultimately a different climate. These cascading effects, each one individually small, accumulating over billions of years, are what planetary scientists call sensitivity to initial conditions. The universe is precise in its mathematics, but vast in the number of possible configurations, and small differences at the beginning can produce dramatically different worlds by the end. Part 9. Other worlds with two moons. We do not need to restrict our imaginations to Earth when thinking about two-moon worlds. The universe is full of planets orbiting other stars, and while we cannot yet observe the moons of those distant planets directly, the physics tells us that multi-moon systems should be common. In our own solar system, as already noted, planets with multiple moons are the rule rather than the exception. Jupiter alone has at least 95 known moons, though most are small and irregularly shaped, likely captured asteroids. Saturn has a similar wealth of moons, including the remarkable Titan, which is larger than the planet Mercury and has a dense atmosphere. The distinction between the large inner moons of the gas giants and the swarms of small outer moons they have captured over time is an important one. Large moons tend to form alongside their planets in the early disk of gas and dust, while small moons are often captured later by gravity from the surrounding space. Earth, because it is a smaller rocky planet with less gravitational reach than the gas giants, would have had more limited ability to capture large moons after the solar system settled down. This is why the giant impact origin of our moon is so important. It was essentially a one-time event that gave us a moon that gravity alone could never have provided. In studies of planets orbiting other stars, researchers have looked for signs of large moons by studying how those moons would affect the timing and depth of the planet's transits across the face of its star. While no moon has been confirmed orbiting a planet in another solar system, the search is ongoing, and the expectation is that they exist in large numbers. Theoretical work on the stability of multi-moon systems around Earth-like planets suggests that two moon configurations are entirely plausible, though the specific requirements for long-term stability place some constraints on the sizes and distances of the moons involved. There is something deeply moving about the fact that we can examine other solar systems and ask these questions, that the same physics that governs the tides on our own beach also governs the orbital mechanics of worlds we will never visit. The universe runs on a single set of rules, and those rules connect us to everything. When we look at the night sky and wonder about other worlds, we are participating in a kind of kinship with the cosmos. We are made of the same elements as the stars. Our moon was born from the same kinds of collisions that shaped every planet in every solar system. We are not observers of the universe from outside it. We are part of it. That thought, more than almost any other, has a way of gently loosening the grip of whatever it is that felt urgent and overwhelming just a little while ago. Part 10. The Moon We Have. After all of this imagining, it seems right to come back to the moon we actually have. The one that rises tonight above every horizon on Earth. The one that has been there since almost the beginning. Our moon is, by almost any measure, a remarkable companion. It is large enough to stabilize our axis, close enough to produce meaningful tides, and distant enough to remain safely outside the Roche limit. It reflects enough sunlight to illuminate the night without overwhelming it. It is, in a quiet way, extraordinarily well suited to the world it orbits. The moon has been studied more closely than any other body in the solar system beyond Earth itself. 12 human beings have walked on its surface. Dozens of robotic missions have mapped it, sampled it, and measured its gravity from orbit. And yet, it continues to offer new scientific questions. Recent missions have confirmed the presence of water ice in permanently shadowed craters near the lunar poles, a discovery that has renewed scientific and commercial interest in the moon as a destination and potential resource. The moon, it turns out, is not entirely the dry, inert rock it was long assumed to be. The moon's geological history is written in its surface. The dark patches visible to the naked eye are ancient lava plains, the remnants of volcanic activity that ended roughly 3 billion years ago. The bright, heavily cratered highlands are older still, preserving evidence of the solar system's early period of heavy bombardment. By studying the moon's craters and rocks, scientists have been able to reconstruct the history of the early solar system in ways that are simply not possible from Earth's surface, where erosion, plate tectonics, and the constant churning of the crust have erased most of the ancient evidence. The moon is, in this sense, a kind of memory, a preserved account of what the early solar system looked like, written in stone, sitting a few 100,000 kilometers away, waiting to be read. There is something touching about that. A world that cannot forget, orbiting a world that constantly renews itself. Every full moon that rises is a continuation of the story that began with a collision 4.5 billion years ago. The same event that could have produced 2 moons, or no moon, or a moon of entirely different character, happened to produce this one, at this distance, with this mass, and the result, slowly and indirectly, was us. Whether you are drifting towards sleep as I speak, or simply letting your mind wander somewhere quieter than wherever it has been today, I hope that thought sits with you gently. The moon above you tonight is 4.5 billion years old. The atoms in your body were forged in ancient stars. You are, in the most literal sense, as old as the universe. And as vast as it is, you belong to it. And on that note, we arrive at the end of tonight's journey through the question of what Earth might have been if only the ancient mathematics of gravity and collision had gone a little differently. We asked what 2 moons would mean for our tides, for our nights, for the stability of our seasons, and for the long story of life on this planet. And in following those questions, we found ourselves, as so often happens in astronomy, arriving at a quiet truth. The universe is enormous. Its timescales are beyond imagination. The forces that shaped our world operated over billions of years through events so vast and so slow that no human mind can fully contain them. And yet, here we are, a small blue world with one large, well-placed moon, a stable axial tilt, and 4.5 billion years of accumulated history beneath our feet. Whatever is weighing on you tonight, whatever felt too large to carry when the day began, try setting it down for a moment against that backdrop. The cosmos has been doing its slow, unhurried work for far longer than our worries have existed, and it will continue long after they have passed.